As he said, my name is Ervin Kraemer, and I'm here to talk to you today about aquifer exploration using seismoelectric GF6 technology. So like many of you, I come from a blue-collar background. My grandfather was in the military in World War II and then went on to work for PMB for about 30 years. My dad was a fireman most of his life, and then actually, among many other part-time jobs, was a helper on a small drilling company, or for a small drilling company in the Northwest. I joined the Air Force in '86 and served in active duty and in the Air National Guard for the last 28 years. Over those years, I've worked in electronics and avionics for both the Air Force and Boeing, and have a physics background afforded to me through some formal education and collision reconstruction work while I was in law enforcement. For about 14 years, I've used, manufactured, and trained people how to use seismoelectric technology, originally invented by two British petroleum exploration geophysicists. Business owners and academics from around the world have used that seismoelectric technology for nearly 2 decades. The GF6 seismoelectric system is the newest version of that original technology invented by Drs. Clark and Miller of the UK, and has been used by groundwater exploration companies and drilling contractors for about the last 2 years, and they're all from all over the world. We have drilling contractors using this GF6 in Australia, New Zealand, South America, North America, Africa, Asia, and Europe. And they use that GF6 to help reduce risk, of course, and to improve overall drilling success. A drilling contractor, one specific drilling contractor in Germany, and a hydrogeologist uses used an earlier version of the system called the GF2000 for about a decade or so, until that system started to kind of break down, as computers do over time. And he then in 2013 bought a GF6 and now is using that to continue his exploration work in Germany. In the handout that's available, that NGWA made available online, there's a paper actually written by that German operator. You can go and download it and read what his 2 cents are on the technology. The GF6 embodies kind of the first major advancement of this technology in over 12 years. It worked quite well up until then, and we just needed to kind of catch up with the modernization of circuitry and software. So we've modernized the user interface, and it's been modified to be easier to use, as well as have incorporated the ability to create automatic simple 2D models of the data collected. So you can take the data, extract it, and model it automatically. Except for training that comes with the GF6, an operator doesn't really need any specialized training or experience. Not that it's not helpful, but it's not necessary. Just about anybody can operate the system. I tell everybody, if I can do it, you certainly can. So here's an example of different techniques that are used for exploration and risk reduction from around the world. And they all have their benefits, and all can certainly be useful in mitigating, I guess, failures. Most of the systems, except for 2, actually image structure variations, and then that's used to infer the presence or absence of groundwater. The 2 systems that directly image groundwater or liquid below the ground are the GF6 seismoelectric system and then NMR, nuclear magnetic resonance. One important thing to remember when you're doing, well, I guess, when it comes to drilling in areas where it's difficult to find good sources of groundwater, any risk reduction is a good risk reduction. So in my humble opinion, if you're only access to resistivity, then I would say use it, especially in very hard areas, because at least it's going to buy you down some risk. But just the thing to remember is that expectations should be set appropriately if you're using other techniques. So as you can see, when you compare the GF6 technology to other technologies that are used for groundwater exploration and to help improve drilling successes, the GF6 presents clear advantages over some of the other ones. One of the operatives of the GF6 uses as a follow-up to testing with controlled source audio frequency magnetolarics, basically a surface resistivity system. That operator used CSAMT to image potential fractured zones. He mostly does it in the Caribbean. And then he follows up with the GF6 to obviously confirm the presence or absence of groundwater. And with the use of the GF6, they've had pretty good success. Well, so far they're 100%, but nobody's 100%, so they'll fail sooner or later. But the reason why they actually went to the GF6 as an add-on to what they've already done is they drilled a very expensive dry production well, and they're a for-profit company, so they obviously can't afford to do that too many times. And using the information provided by the GF6, they've improved not only the overall success rate, but also have improved the actual final results of the yield of the wells, because they can look at variations. So the GF6 can tell variations in potential because it only sees liquid. It can see the variation of that water and see strength or weakness, and sites could be picked based on that as well. So one of the questions that I get frequently is, where does the GF6 work best, or where doesn't it work? So the best way to answer that is really talk about where it doesn't work well. All techniques have their limitations. Seismics, deep testing with seismics, you have a limitation of area size. If you want to look down to 10,000 feet, you've got to have 20,000 feet of of seismic lines, more or less, to see that deep. So every system has a limitation. Our limitations are based primarily on surface conditions and in some cases electrical interference. So where surface conditions come into play, we need native testing conditions or undisturbed testing conditions, soil. We need about 3 feet of it. So non-native would be something where you have areas of fill or areas where you have deeply turned soil. Now it can be done in both of those, but it doesn't work as effectively. You get a loss of seismic energy in tilled areas or filled areas, so you lose some of that energy that you're trying to create to image the aquifer below. And it also impacts the ability to get repeatability, which is critically important for any kind of technologies. You want that repeatability. So to overcome fill areas, I did a project up in Canada where they had a large area that had about, I don't know, it was maybe about a quarter square mile area that had preload on it. They were preloading for a construction project. Well, it was about 5 feet deep, and it was just pit run, which I couldn't have done anything with because we need actual dirt. So they brought in an excavator and actually removed the pit run over 28 areas. They just did big, deep ditches about 5 feet down, bringing us down to the native soil, and then we did the testing and everything was fine. So it can be done, you just have to move the non-native material out of the way. Another area that can be complicated is where you're near high tension power lines. So in the image here, basically I wouldn't be able to do it right next to those power lines. I have to be some distance away from those because of the interference. It doesn't present false positives, it just makes interpretation extremely difficult, and repeatability is very hard to obtain when you're in noisy situations. Electric sources like residential power or even secondary transmission lines don't really impact the GF6 unless you're right on top of them, or if you're at an intersection. Where you're at an intersection of electrical interference, you get two frequencies or more, and it's hard for the system to filter it out. It's designed quite well it's designed well to filter out electrical interference when you have multiple frequencies. You only get one. You can only take one main frequency out. The balance are left over, and that's where kind of confusion, but again, not false positive, just simply a difficulty with interpretation. So the GF6 can be used on very small focused sites. Most operators don't do less than 5 test sites on any property. We do operators do a lot of work for domestic wells because it's affordable. There's not a lot of overhead bringing the system in. Once the system's owned, you can do work just about anywhere and actually afford to do it. That's one of the nice things about the GF6 is it makes it really a geophysics technique available to everybody, pretty much. Or you can do it on large exploration areas like the one on the lower right there. That one we imaged most of about 300 acres and did about 225 sounding sites. And then that data can be used to do any number of things. You can do 3D modeling with it, 2D modeling with it. You can do all kinds of, you can do a surface image showing sort of variations within the zone. It's quite amazing what you can do with the data once you do collect it. So on larger properties, when we're doing work on large properties, we typically don't do this type of saturation in the lower right. What we'll do is we'll do more of what we call preliminary survey, do wider separations in the data, then pick hotspots, high points where there's best potential, and then we'll go back and focus some soundings on those areas just to confirm it and to get some more detailed yield assessment on those. So here's an example of a project we did in eastern Washington. And just to go back, the GF6 has been used in all geologic structures. You name the structure, we've done some work in it, or operators have done work in it. This is an example of a granitic area where you find granite at depth, probably about 10 feet down, you're in granite, and you're in granite until you're tired of drilling, pretty much. In this area, it's quite difficult to find water. I mean, a good well might be 2, 3, 4, 5 gallons a minute. And the property owner that had our team come out obviously knew that and wasn't willing to do exploration by drilling, because in Washington, drilling's somewhere in the neighborhood of $30 some odd a foot just for the hole in the ground. So it can be expensive to look down 400 or 500 feet hoping you hit water. So we came out and did a small project. We just did 5 sounding sites in a linear pattern, and then we processed and interpreted the data later and provided yield estimates. Our estimates were a base of approximately 280 feet at the site they drilled, with an estimated yield of about 2 to 6 gallons a minute. The resulting well, actually, they encountered water at about 309 feet, so we were off by about 29 feet, more or less. And then the estimated yield, the final yield, was 6 gallons a minute. Honestly, it's hard for me to imagine doing better than that. The system's quite good at domestic volumes and can be used very effectively in agricultural projects. You just need calibration for those types of things. So here's an example what the data would look like if you captured it and just kind of stacked it in a very simple image. So on the left is really what any operator would look at out in the field. The only difference is the green lines, I put them in there. So the green lines kind of show roughly the permeable zone where you see them. But one thing that I'm display this for is that you can see the repeatability. It's quite easy to get repeatability, and the way the software works is it just stacks the data. You just hold the data windows open, and so once you're done with your soundings, you can actually scroll through them and see those consistencies or the inconsistencies and determine if more testing is necessary or if you can just drive on and finish the project. On the right is just a real simple 2D model showing what the permeable zone would look like if you modeled the data. It's just a good illustration if you want to do it, and since it's automated, it's quite simple to do. Here's an example of a project we did in Montana. It's up, if anybody's familiar with Flathead Lake, it's above Flathead Lake. It's about 500 feet off the lake surface up on a hill, or if you're from the Midwest, a mountain. What we went up there not knowing anything. There was no wells up at that elevation. The closest well is about 2 miles away. So we went up. I can tell you the access was sketchy. I was actually concerned how we would get a driller up there, because I wouldn't have wanted the guy to bring a big old drill rig up on top of this mountain, but he insisted it could be done. So we did the testing. All of our testing was done remotely, so we had to pull all of our equipment out of the truck and hand carry it in because we couldn't actually drive to the site. We did the testing, and then the final resulting yield, actually originally we provided them with a yield based on what we believe to be true about the geology. The tough part about this area, because of the lack of well logs and detailed USGS data, we were under the impression, based on what we got from the driller, that the formation would be kind of brittle limestone. That's what the formation was. So we assumed it would be a little softer than it ended up being. The driller drilled 500 feet and it was just hard material, no cave-ins, no problems, just nice clean hole. So we backed up and we reassessed the data real quickly, gave them just an updated depth. We didn't change the yield. We updated depth to 740 feet instead of 570 feet. And they continued to drill, and the drilling contractor indicated he had encountered water between about 669 and about 750 feet, something like that. We told him 5 to 10 gallons a minute, and he ended up with just better than 20. The driller put 20, but 20, 10, not relevant, since both are enough for a domestic well. Again, this is an example of the data on the left, or the data stacked just side by side, and you can see the repeatability that we encountered up there. And then on the right is a 2D image just created with the modeling software that's included. So kind of one of the easiest uses of the system is to determine the max depth. So in this case, we did a huge project on a northwest Texas farm, about 100,000 acres of land. And we probably did some work. My son was out there. He did work for about 8 months. And we provided him with data on various quarter sections. And these are just an example of 3 of the sites they drilled. So you can see where the red lines are the approximate zone that the drilling contractor indicated they encountered water. So they started encountering water where the red line starts, and then the bottom red line was the bottom of the water. The green line indicates where we said to stop drilling. So you can see where the data shows that permeable zone or approximate thickness, and then they probably stopped just above that the green line. So when they went out of the permeable zone, when they stopped drilling. Nonetheless, our estimates were reasonably accurate, and they were quite happy with it. In fact, they're going to expand their project here soon and go on more of the 100,000 acres. You can imagine the daunting task of drilling wells on that much land. So one of the things the GF6 can do is determine multiple permeable zones. So it doesn't just see one zone and that's it. It sees multiple zones. So in the example on the left, there's a shallow, a glacial zone. So there's unconsolidated material. And then a deeper zone in a primarily a basalt interface. And you can see where the two zones are painted just by the green lines. Now, right, it's a project in Oklahoma where they actually had a very deep well drilled for municipal use or rural use. And you could see where the zones were painted. So the first set of green lines are the first zone, second zone, and third zone are indicated. The deepest zone was, well, 430 meters, about 1,400 feet deep. So we can also determine thickness. With enough data collection and good quality data, you can give approximate thickness, sort of roughly the beginning of the zone and the end of the zone. This typically paints the zones in a macro view, so it doesn't see those small permeable zones. Say that you have a 100-foot permeable zone, but there's maybe 10-foot sections that actually produce most of the water. We don't see those as individuals. We see those as a totality of a zone. Right. Another thing, obviously, it can be used for is estimating yield. So with the processes built into the system, all the software is included in the system or part of the system. So using the software to process the data, you can determine minimum expected yield. In a worst case scenario, it'll be minimum expected. In a best case scenario, when you can have calibration, where you can calibrate to a known source within a mile or so in the same geology, you can actually provide quite accurate yield. In fact, one drilling contractor bought the system because of the success he had when he was contracting the service out. So he contracted the service out for about 3 years to an operator in Walla Walla, Washington, and then ultimately decided to buy the system because of the success in agricultural projects. And as most of you guys know, in an agricultural project, you have to be pretty right on with yield if you're going to give yield. If you say it's 10 gallons a minute and they get 1,000, they're not going to be happy. First of all, they wouldn't even drill for it. So you may stop them from drilling where they might otherwise drill. So using calibration, we can use this equipment to adjust those sites, adjust that information and get accurate yield estimates. So to wrap up, there's a number of things the GF6 can be used. Again, it needs good testing conditions, proper operation, but it can determine maximum depth. It can provide estimated thickness of the zone, minimum expected yield in a worst case scenario, or a very accurate yield if you have the right information. And then you can also derive permeability, porosity, and transmissivity out of the system. Now, the system can be used as a complement to other geophysics if you're using it, or a standalone system. It just depends on what you do with it. We have operators from just about every walk of life using the system, whether they're drilling contractors or just somebody that thought they would help somebody out. And that pretty much does it for me. If you guys have any questions, I'm happy to answer. I think I have maybe 2 minutes, something like that. Yes?
Approximate cost of the system?
So a GF6, the average cost is somewhere in the neighborhood of $24,000 to $25,000. That includes training for one person and pretty much all the things that you're going to need to do the operation. The 2D modeling part is really optional because not everybody cares about it because it displays those graphs right there. So most operators just use the graph as so that their visualization of it. Some people like the 2D, and the industry, some parts of the industry require it. So about $24,000 to $25,000.
And what would be an approximate fee for a 5-acre project?
So I'll speak to that based on what other operators tell me. So if somebody was going to do 5 acres, they wouldn't first of all map the whole 5 acres. They would map some portion of it because there's no point. There's not going to be enough variation over 5 acres to do the whole thing. So typically they'll run a line through the 5 acres. So it might be, I don't know, $2,000 to $3,500 maybe. Typical domestic wells, from what operators tell me, range from around $1,500-$1,600 to about $3,000, more or less. And then obviously bigger projects, ag projects are much more expensive because there's just more land to test typically. So, yes.
What kind of modeling are you doing to create those 2D panels?
So because the output is permeability or hydraulic conductivity, we just take the hydraulic conductivity, export it. It's just processed, so we just export it and then import it into Surfer.
So it's really more of a graphing than modeling.
Yeah, I guess you would say that's probably, I suppose, accurate because we're just taking the data and plugging it right into a 2D model. It can do, or a 2D, I guess, display. Yeah, it's an illustration. I look at 2D, any kind of thing like that as just a really nice looking illustration of the data that was already collected. Yes?
Yeah, on a 160-acre
Mm-hmm. Uh-huh.
What would that assessment cost?
160 acres. What's that?
How many holes would you do?
I think it would be 160 acres. You probably run, because I would corner to corner it. I would, if it's a square quarter section, then I would run it from one corner to the other. I would just run a straight line right through the corner, and that might take 12 to 15 sounding sites, something like that. They're typically separated by about 100 feet or so. So whatever that hypotenuse is the, if you divide that by 100, that's the approximate number of test sites. That would probably be better off as a day rate, so it would probably be $4,000, more or less. Thanks for your attention.